I'm in. Hello, hello. I'm in the classroom number 7. Yes. Check in the meeting if the screen is visible or not, and I am unmuted. That's one more thing we need to check. Okay.
My audio is not on. Someone is muting me. That's why it's the problem. I need to change those settings. Because I created this meeting in a little hurry, that's why. Yes. Okay. Before that, my audio is still on, right? Yeah. Yeah, my audio is now on and screen is visible. Okay. Okay, that's the best thing that we can worry about. Is recording is started already. In terms of automatic recording. So the last lecture we were discussing calculating calculating particular integral for the equations of the type some f of b some f of b times y is equal to p of x. Right. We're calculating the particular integral of the equation of this type. The particular integral had the form 1 upon f of b times q of x. And we are trying to find the meaning of that word, that quantity 1 upon f of b. So we discussed that for if my right hand side is q of x is e to the power ax, in that case 1 upon f of b into e to the power ax turns out to be 1 upon I will say f power k. I will take the k derivative directly because that's the multiplicity, right? So I will directly write down the generic form. Then second case, when my q of x is trigonometric, cos ax or sin ax, for shorthand, I will say trigonometric of ax. In that case, 1 upon f of d, this trigonometric of ax was written as some g times b square of trigonometric of a square. We converted the function, consider the function of b square only, and then we calculated it as e to the power k of d square into x to the power k dA of x, where again k is the multiplicity of the root, but multiplicity of the root corresponding to the trigonometric ones are ia, not just a. Right. So here k is the multiplicity of the root a, and here this k is the multiplicity of the root ia. Okay, a may not be the root, but ia will be the root. Okay, and the last thing that we will discuss when q of x was some monomial x power n. Right. When q of x was a monomial. So in that case, 1 upon f of d into this x power n was written as fd of fd inverse of x power n, where we expand fd inverse ug the following formula: 1 upon 1 minus u as 1 plus u square plus u cube and so on. Right. So again, I will discuss some examples of this type. Okay, I will discuss some examples of this type. This d square. Yeah, there's the d square. I forgot to write down the replacement. The replacement was minus a square. Right. Thank you. So the d square was replaced by minus a square. Okay. I hope for a while this mobile works so that I can at least find some questions. I'll give it a try. So consider d power 4 plus 3d cube plus 2d square of y plus x square plus x. I guess this is not one of the problem which is discussed. I'm just putting it up randomly. Okay. So what will be my complementary function? Notice that 0 is a repeated root and repeated for twice. Repeated for 2 times. So corresponding to the 0, I have C1 and C2 x. E to the power 0x I am ignoring. Because e to the power 0x is 1. Okay. And what are the other two roots? What are the other two roots? Minus 1 and minus 2. Right. So it will give me C3 minus x plus C4 e to the power minus 2. Right. I hope again you know how to calculate this complementary function. Now, to calculate particular integral, what we can do, we have to calculate it as pi as 1 upon f of d times q of x. But in my case, f of d is d square times d square plus 3d plus 2 times x square plus x, right? So what I will do in this case, I will rewrite this as d plus 2 and d minus d plus 1 of x square plus x. X square plus x. Okay. Why I am doing this? Because I want to show you the third type of solving this problem. Again, there should be something new for you guys who are coming further again, right? So I'm just showing you the third way to solve the same problem. Okay. So what I will do, I will ignore this part and I will focus on d plus 1 of x square plus x. Right. I'll operate this one later. So I will operate this d square and d plus 2 later. And I will focus on operating 1 upon d plus 1 plus d on x square plus x. I'll focus on operating 1 plus d on x square plus x. Right? Now, what is 1 upon d? 1 upon 1 plus d using the previous formula. Instead of plus, it will be minus. So there will be alternating plus minus signs. Right? So expand that. You will get 1 upon d square d plus 2 as it is. Expanding this bracket, you will get 1 minus d plus d square. Should I write down d cube? No, because we have quadratic polynomial. So if we taking the third derivative, we give the value c. Let's stop here, and I'm taking this for x square plus x. Now evaluate this quantity. You will get 1 upon d square d plus 2 of what is 1 times this bracket? Simply x square. I will consider x in my mind for a while. What is differential of this bracket? Okay, otherwise I will write down all the terms. What's the harm? So it's 2x minus 1 and this square will give me plus 2, right? So this one is 1 times minus d times and minus plus d square times of the bracket. We can rewrite this as d square d plus 2 of this will be x square, this will be minus x and plus 1, right? Right? Again, follow the same procedure for d plus 2. Take 2 outside, so that it will be d by 2. Right. Take 2 outside, so 2d square. I'm operating 1 upon 1 plus d by 2 on x square minus x plus 1. I'm operating 1 plus d by 2 on that expression. Okay. So how I can operate? 1 upon 2d square. Again, I will expand this to the cubic expression. So I will get 1 plus not 1 plus 1 minus d by 2 plus d square by 4, and I will stop here. I'll again stop here. Why? Because your cubic expression, I am having a quadratic equation. Quadratic expression on my right hand side, and taking the third derivative will give me the value 0. I will have x square minus x plus 1. So I will copy this part. I'll copy this part and move on to the next slide to calculate it further. I know this actually involves a lot number of steps, but those steps are actually quite easier to evaluate. Okay, this involves a lot. I mean, breaking down the problems into small steps and then evaluating the small problems. Okay, that's the focus on this method. So this will be 1 upon 2d square. Calculate 1 times this bracket is x square minus x plus 1. D of this bracket will be minus of 2x minus 1 by 2, and d square of the same bracket will give me 2 by 4. Right? Now I will have 1 upon 2d square, x square as it is. This will be minus x, which will be minus 2x, plus 1 and plus half, which will give me value 2, right? 1 is plus half and this plus will give me the value 2. Now, what is the interpretation of d square, 1 upon d square? It will be double integration. So integrate this quantity or twice, or I'll integrate for once first. So I will get x cube by 3 plus minus x square plus 2x, and again integrating to remove this d, I will get half times x power 4 by 12 minus x cube by 3 and plus x square. Okay, this board is again not supporting, but consider I have written x square. So notice that this will be my particular integral. This will be my particular integral. Okay. Again, this is not my complete solution. My complete solution should be complete solution is y is equal to CF plus PI. Whatever that CF was, just copy that part. I will copy that part. Turn off automatically. Okay, this is same. So where we, I want to copy the CF part and I want to paste it here as my CF. Okay, suppose should be visible fully. And again, I want to copy my PI and paste it again here with the addition sign in between. Okay. Right. So this is my complete solution. So what we have done, we have break the problem into small chunks and then we evaluated the problem. Okay. This method can be also used. So we have discussed three different methods to do the same problem. Okay. We have discussed three different methods. Again, which method to choose is up to you. Well, I will discuss the, here I have explained something part of expansion part. So I will consider a problem with method of undetermined coefficient, those AX, writing down it as AX plus B and all those things. Okay. So give me a quadratic equation which can be solved. I will go for X square. Give me a quadratic equation. In D. So D square minus 4D plus 4. Plus 4. Okay, so it is expansion of n minus 2 whole square. So 2 is a repeated group. So it will my C of will be C1 into the power 2x plus C2 x into the power 2x. Okay. So if my right hand side is a degree n polynomial, I'll assume that so my particular integral is yt is equal to a quadratic polynomial. In case ax square plus bx plus c. Okay. So if my right hand side is a degree n polynomial, I will assume that it's a degree n polynomial as my particular integral solution. Okay. Now, can I calculate yt dash? I can calculate it as 2ax plus b. And I can calculate yt double dash as 2a. Right? So I'll substitute these values in my given equation. So d square, that is 2a plus, not plus, minus. I'll write down the signs corresponding to them respectively. So 4 times b and minus 4 times of this one is 8 times ax. And well, 4 times of my particular integral. It will be 4 ax square plus 4 bx plus 4 c. This should give me the value x square, 1x square plus 0x plus 0. Right. Comparing my left hand right. I have substituted this as I use a different color. So I have substituted here y double dash, then here minus 4y dash, and here 4y. Okay. And I am comparing the coefficient. Comparing the coefficient, what I can get? Comparing the coefficients, I will get 4a is equal to 1, which will give me value of a as 1 by 4. Right? And comparing the coefficient of x square, 4a should be 1, which will give me a as 1 by 4. Now, I will compare the coefficient of the x, then I will get minus 2 plus this 4b, this should be 0, right? I'm substituting a as minus plus 1 by 4. This will be minus 2 plus 4b should give me the value 0. So this will give, by solving, I will get value of b as plus half. Value of b as plus half. Now compare the constants. 2 times a, which is 1 by 2, minus 4 times 1 by b, minus 4 times b, which is minus 2, because value of b is minus half, plus half, and plus 4c should give me the value 0. So 4c should be 5, not 5, 3 by 2, and this will give me value of c as 3 by 8, right? So I got my coefficient. So I'll rewrite my particular integral as the particular integral in this case. In this case, is yp is equal to, what was the value of a? It was 1 by 4 x square, then plus half x, and I guess 3 by 8, right? So this was the value of particular integral. But again, notice that this particular integral is not the final solution. You have to write down your final solution as CF plus PI. You have to write down your final solution as CF plus PI. Okay, I guess that's enough for the last section. We can compensate the missing audio part. Okay. In which example? I forget what we need to do. Yeah. Yes. Okay. Whole base change, right? Yeah, I was explaining and I stopped. So remember the law, base changing rule. So AB is equal to can be written as, if I want to change the base to C, from C, what can I do? Log of uh, log CB divided by log CA. Right. Now suppose this B is some a to the power, some a to the power x. Okay. So if that B is a to the power x, then this will be log C of b to the power x, right? Sorry, a to the power x. This will be a to the power x and divided by again log c to the base power a, right? Now I can cancel out this, so my x will be log c a to the power x. Again, I not well. I thought I've seen one problem like this, but well, how what they have done? That 2 to the power x is replaced by e to the power log 2 times x or something like this. Well, I don't remember the exact changes that they have done. But by taking log only, they have done something. Well, did it? Okay, consider I'm going for e to the power a. So suppose there is a to the power bx, and I want to convert it as, or I want to see it as e to the power some cx, e to the power some cx. Okay, I want to find out that value c. I will take the log both sides. I take the log both sides and log to the base e. Okay, if I am taking log to the base e, I will have bx into ln of a is equal to cx, right? So therefore, value of c should be uh, b ln a divided by, no, nothing divided by, right? Only BLNA. Okay, this is the change. Okay, this time randomly that worked. Suppose my right hand side again. Suppose this previous example 4D plus 4y is equal to. Suppose I am having here let's say 5 times 4x. 5 times 4x. What I will do? What I will do? I will try to convert this into some e to the power some by some linear change. Okay, by some linear change, I'll try to convert this, or I will try to look this as e to the power some cx. So what I want to do, I want to have 5 to the power 4x should be e to the power some cx. Again, I will take the log, take natural log. So you will have 4x ln 5 at cx. So value of c is 4 ln 5. So I will convert this problem as the left hand side is same. There is I haven't changed, but instead of writing 5 to the power 5 to the power 4x, I'll write it down as 4 ln 5 times x. Okay, that's the change. And then you know it is e to the powers of ax. And you know how to operate. Okay. I should have thought about this one first. Okay, there was one problem which I thought just by converting it can be directly solved, but I forget how. Well, I haven't tried that one before coming to the class, and that's why I got confused. Here also I haven't solved it, and this is what I do before coming to the class. Trial and error, and whatever the method that works, we explain. Again, the third method that we discussed, the first method in this lecture that we have discussed was occurred me when I was talking about the fifth method. Fifth method of solving these regular equations. So fifth method is general works for in general things. If you are right hand side, well, notice that we are discussing on some specific right hand sides. So what will happen if my right hand side is a general thing? So fifth method works for such types of problems. Such types of problems. But the best part here was that while discussing that, I thought I could use it to the third problem, these polynomials, and this could be really easy. So it's just a variation of the fifth version, fifth method that we are going to see. Okay. So before moving to the fifth method, let's start discussing about fourth method. So in this case, my q of x, my right hand side, will be e to the power ax times some phi x. Okay, e to the power ax times some phi x. Okay, so my equation will look like some f of t times y equal to e to the power ax times phi x. Then in this case, my particular integral should be 1 upon f of t times e to the power ax phi x, right? Phi can be any function. Phi can be any function. Mostly it will be trigonometric or polynomial. This can be written as, I can take this thing outside e to the power ax. I can take this thing outside the operator. But notice that was a function. It's not a function which can be taken outside without any cost. So the cost of taking this thing outside is you have to change your operator at t plus t. Okay. The cost of taking this e to the power ax outside the operation is to change your operator from f of d, 1 upon f of d to 1 upon f of d plus a. So I need to pay this plus a charge of phi of x, and the rest can be calculated. This is now outside the operator. So we don't need to do any integration, differentiation, anything. We have to operate on my left hand side. Okay. So again, because I want to focus on polynomials more, we can have trigonometric functions also as my right hand side, but I will go for polynomial. I'll go for polynomial. Okay. So consider one problem. Consider a problem. Uh, d square minus 4d. This time I will go for plus 3 so that I am having different roots. Times y is equal to e to the power 2x. Which polynomial should we take? Let's go with x so that I can explain the this method more dominantly. Because for x cube, the first method definitely is going to fail, will not work nicely because we have three terms on my left hand side. The second method, the comparing coefficient method of undetermined coefficient, will also give me an expression to find out four constants A, B, C, D. I need to calculate four constants A, B, C, D. So that will not be that much good. That will involve also more calculation. So in this problem, the third method that we have seen today will work really great. Okay. So how? Well, definitely we must start with calculating C. What is C of? C1 e to the power something and C2 e to the power. Well, both the what are those? 3x and x. Right? 3 and 1. Right? 3 and 1. Now calculate particular integral. Notice that even I am not writing here. You are supposed to write down the expression for here. You have to extract the auxiliary equation, equate it with zero, calculate the roots, and depending upon the nature of root, you are writing here. Okay. Even though I am writing CF directly just to save the time. For you guys, you have to write down in the exam, you have to write down the full explanation of CF. But there are just 3 to 4 lines. But you have to write it down. Now to calculate PI is given as 1 upon d square minus 4d plus 3 of e to the power 2x into x cube. I will take this e to the power 2x outside my operations. I will take this or I will write it down first as d minus 1 and d minus 3 into e to the power 2x of x cube. Okay. And at this stage, I will take e to the power 2x outside my operation. At this stage, I will take e to the power 2x outside my operation. Why I am writing down this step? Well, this is unnecessarily. I would have replaced d by d plus a with the previous step. But why I am writing this form? This will be simplified, right? Calculations will be simplified. Otherwise, I have to go for d plus 2 whole square, then minus whole d plus 2, and I need to solve the brackets. Then again, I need to factorize because I want to use the previous method, which uses the factorization form, factorized form. So better to go for the factorized version first and then substitute d for d plus a. What is the value of a here? 2. So instead of d, substitute d plus 2. So you will get 1 upon what is d plus 2 minus 1. It will give me d plus 1 and d plus 2 minus 3 will be d minus 1 x cube. Right? So again, I will copy this part and move to the next slide. And I will again use repeated version repeated version of the previous expansion. So I can consider this as e to the power minus 2x 1 upon this 1 plus 3 as it is, but here I will change reverse the order. So 1 minus so that I can compare it with 1 upon 1 minus u and x cube. That's why here extra minus is added. So minus e to the power 2x times 1 upon 1 plus d. And what is the expansion of 1 upon 1 minus d? 1 plus d square plus d cube. I need to go for till d cube this time. Times x cube. This will give me minus e to the power 2a. Better than that, I can say that 1 plus a, 1 minus d. What is the 1 plus a plus b and a minus b? 1 minus b square, right? I guess this is much better, efficient. Well, notice that we can figure out some steps which are quite easier to evaluate while solving the problem. So that's why there are so many words. This will give me minus e to the power 2x 1 upon 1 minus b square of x cube, right? A plus b and a minus b will be a square minus b square. So 1 upon 1 minus b square. Now I will expand 1 minus b square. So instead of u, what I will consider? U square. This will give me 1 minus e to the power 2x into 1 plus u plus u cube u square. In this case, it is d power 4. But what is d power 4? D power 4 of x cube? 0. So I don't need to consider later terms. X cube. So this will be e to the power 2x x cube plus 2. Second derivative, 2 times derivative of x cube will be 6x. So this is my particular integral, not yet complete solution. Write down your complete solution as complete solution is y is equal to cf plus pi. Add those two whatever the values that we have. Cf plus pi. Okay. So I guess we have not much to talk about the fourth one. Again, this uses the previous facts, previous methods, but more dominantly, except the fact that we can take e to the power a outside the operations by the cost of having d. By the cost of having. So replace d by d plus a to remove that e to the power ax outside the operations. That's your fourth one. And now the thing which will work in general is, so if my q of x is any general function, any general function. So in this case, I am not restricting my q of x. It won't have any particular form, right? It won't have any particular form. So in that case, how do you evaluate? So notice that the given equation always says it is f1 upon f of d times y is equal to q of x, right? But this f of d can be written as some d minus m1 into d minus m2 and so on till d minus mn times y is equal to q, right? We can expand them. Now I can calculate my y. Calculate my y. I need to take the product of a going from 1 to n, 1 upon d minus mj of q. Right? I'm just writing down in the shorthand notation. But I know whenever I will see a polynomial seeing in the denominator, what we generally try to do to integrate, which is the method that we use for more, which method do we use as a more dominant method to integrate something when polynomial is in the denominator? By parts or partial fractions, right? We try to go for partial fraction. So by partial fraction, will I be able to write down say j going from 1 to n again with some coefficients aj corresponding to them times again d minus mj of q of x. Will I able to write down this? Again, yes, if my roots are distinct. No, if my roots are not distinct. In that case, my expansion will have this term power square. Right, power square, power till the power k till it is repeated. So in that case, what to do? Or anyway, I am not going to ask such repeating root problem in the exam, but still, I will explain what to do if my roots are repeated. Okay, for a while, consider all the roots are distinct. All the roots are distinct. So I can do this, right? I can do this. Now, notice that this is a separate problems. My particular problem is to calculate my yj as 1 upon aj times d minus mj of q of x, right? And summation of all yj's will give me my complete y, right? I break down my problems into again small parts. Like the previous one, we have break down our part in third method of polynomial. We break down the problem into small parts, right? So that's what here I am using. I'm breaking down the problem into small parts. Now I have break down my part problem into small parts. Now how to solve this small part? Notice that this equation is satisfied by some y times. Let's forget about this aj for an hour because that's a constant. We can manage that. So mj of q of x, which is some d minus mj times y is equal to q of x, right? This is the equation satisfied by y. But what is dy? dy by dx minus mj of y is equal to q of x. This is the equation which is satisfied by y. Can you identify that equation? It's a order 1 degree 1 linear differential equation, which we have studied till now, right? This is a degree 1 order 1 linear differential equation. To solve that, we need to calculate our integrating factor. What is integrating factor in this case? E raised to minus mjx integration of mj is a constant, right? So integration of mj dx is mj into x. So my solution will be y times e to the power minus mjx is equal to integration of e to the power minus mjx into q of x dx, right? So I can rewrite this solution, the whole solution as y is equal to e to the power mjx into integral of e to the power minus mjx into q of x dx, right? This is my small component yg, not whole y, but some component yg of my solution, right? Again, nobody is going to ask the derivation. You're supposed to remember that big formula. Okay. So, what is my conclusion? My conclusion is 1 upon d minus mj of q of x is e to the power mjx into integral of e to the power minus mjx into q of x dx. This is my conclusion. And this will be my rule number 5 for generic functions. Okay. So whenever I am having generic problems, I will use this formula. So whenever I can't see anything similar to my first four formulas, first four rules, I'll try to go for this one. Again, since we are having a generic rule, why do we go for discussing about the first four rules? That should be a question, right? So think about the quadratic equation. Do you go for quadratic formula directly? No. Why? Why don't you go for quadratic formula? When it solves all the questions, why don't you go for quadratic formula? We have easier alternatives. So that's why the first four were easier alternative for this one. But again, those alternatives won't work for every problem. They don't work for every problem. That's why we'll consider this as our last resort to write down or to get our solution. This will be our last resort. This will give me the solution for every case, but this will definitely involve lots of calculations. This will involve lots of calculations. Okay. So let's see an example. So I hope at least. Okay, this is actually playing that my mobile is also playing with me. Where are those rules? Consider this problem: d square plus 4 times y equal to tan 2x. D square plus 4 times y is equal to tan 2x. Okay, we will try to we will extend till for 15 minutes. Okay, we'll end the lecture at 10:15, so that we can cover complete this problem, and I can just say that fifth rule is done. Okay, by discussing only one problem. Okay, first thing that we always do is calculate here. My roots are complex. Which what are complex roots? 2y and minus 2y. These two are my roots. In this case, my CF is given by C1 cos 2x plus C2 sin 2x. Why? Because there is no exponential part. So if there was a real part, that will come as the exponential part in the roots. So e to the power ax times C1 cos bx plus sin bx. Here the value of a is 0. There is no real part in the roots. My roots were 0 plus or minus 2y. 0 plus or minus 2y. Okay, so that's why my CF is given by C1 cos 2x plus C2 sin 2x. Now, calculate my particular integral. I need to go for e square plus 4 times tan 2x. Tan 2x. Well, even if it's a trigonometric function, I can't see it as a really simpler trigonometric function like sin and cos. Okay. So for this time, I have to go for my other roots. So I will expand this as t. What were my roots? Minus 2y and plus 2y. My or in other order, in reverse order, whatever. Right? So 1 upon b minus 2y into b plus 2y of tan 2y. That's what I have to get. Again, I can't focus on this smaller version directly. So I will go because even if I am integrating tan 2x directly by taking the using the previous rules, again I need to integrate the bigger quantity. Whatever I'm getting for integration of tan 2x, and it will be some long model. So what I will do, I will separate out the terms. So I'll consider 1 upon t minus 2y into t plus 2y as some a times t minus 2y plus e times t plus 2y, which will give you one should be a times t plus 2y and b into t minus 2y, and by a certain calculation I will get a as I need to remove b, so minus 2y. I need to substitute d as 2y, so this will be a will be minus plus 1 by 4y, right? Instead of b, substitute 2y. And what will be the value of b? I need to remove b, a. So instead of b, I need to substitute minus 2y, right? If I substitute minus 2y here, this will be 0, minus 2y, minus 4i, which will come in the denominator. So it will be minus 1 by 4, right? 4i, right? Minus 1 by 4i. I by 4, okay, I by 4. Yeah, yeah. Minus of this will get considered. Okay, that's fine, but I will take this 1 by 4 4 common. So I will write it down. My particular integral as 1 upon 4i times, so that I can take that outside. Instead of writing I by plus I by 4i, I'll still go with minus 1. So 1 upon 4i, 1 upon t minus 2i minus 1 upon t plus 2i times tan 2x, right? I'm just substituting the values in this equation. Here, I'm rewriting this expression as that one. Okay. Now I'll again focus on the smaller version of the problem. This one. Consider 1 upon t minus 2I of tan 2x. This is the smaller version, right? Ignore that 1 upon 4I for a while. So 1 upon t minus 2I of tan 2x can be evaluated as, using the previous formula, this bigger one. You have to write it down e to the power mj. If it is minus mjx, so it is minus 2I e to the power 2 ix, right? E to the power mj into integral of the negative sign as it is into tan x, tan 2x dx, right? But I know the expansion of e to the power I theta. What is expansion, or what is the simplification that we generally use? Cos theta plus I sin theta. In this case, I am having minus 2I x, so it will be, keep that as it is and write it down as sin 2x divided by cos 2x into, this will give me cos 2x minus I sin 2x dx. Okay, I sin dx. And okay, I need to integrate, right? Integration of this one. So this will be e to the power 2ix integration of cos x and cos x will be cancelled for the first term. So integration of sin 2x minus I times, this will give me sin square 2x divided by cos 2x dx, right? Right. Now to the power I 2x into integral of, again I will write it down as sin 2x, but this I will write it down as minus I 1 minus cos square 2x divided by cos 2x into dx, right? Instead of sin square 2x, because I can't go for any substitution. I cannot substitute anything like sin 2x dx as something or some dt for it. So I'll expand that sin square 2x as 1 minus cos square 2x so that I can cancel out the term. So again, I will have e to the power I 2x or 2ix into integral of sin 2x minus iota times. First one will give me sec 2x and second one will give me minus. Okay, I am taking minus iota common. Okay, so minus, but that doesn't matter how you are writing. Sin cos x dx, right? Now integrate the values. Integrate the values. You will have 2ix. The integration of sin x, sin 2x dx will be cos 2x by minus 2x, right? Integration of sin is negative. Then I times, what is integration of sec 2x? It will be log of sec 2x plus tan 2x by, again 2. Notice that there is a negative sign here, and this negative will become positive, and I times cos 2x. Integration of cos 2x is I times sin 2x by 2. Okay. So this is my, I will call something like pi1, because this is not the complete particular integral, but one part of my particular integral. And what is the other part? What is the other part? pi2. What is my pi2? That is, I just notice that pi1 and pi2, I consider this part with not without this negative sign. So the only change in pi1 and pi2 is iota is replaced by, and minus iota is replaced by plus iota. or iota is replaced by minus iota. Okay, I am considering this as plus iota. Then this will be minus iota. Minus this one will be plus. I just consider this as G. So whenever I will see I just replace that by minus I because it's a constant. So they will carry out their sign as it is, and everything will be same because they are same constants. So by looking at the above solution, I can write down the Pi2 as minus 2ix. Here there is no I, so minus cos 2x by 2. Then here there is I, so plus I times log of sec 2x plus tan 2x by 2. And here again there is I, so I need to change my sign as minus I sine 2x by 2. Okay. So what is my complete solution or complete particular integral? My particular integral is 1 upon 4I times pi1 minus pi2. Right? Particular integral 1 minus particular integral 2 times 1 upon 4I. So substitute the values. Notice that I can take this minus cos 2x by 2. Then take that common cos 2x by 2 minus cos 2x by 2. From pi1, what is the thing which is remained? This term, which is e to the power 2ix, and minus from pi2, this term is remained. So minus 2ix, and notice that there is extra 4. I need to multiply by this one, right? So it will give me 2 into 2i. There is a reason that why I am writing like this. I can consider this as sine 2x. Okay. Then plus, I'll club the other terms. Other term is this one. Okay. The other term is sine 2x minus I times log of sec 2x plus tan 2x whole divided by 2, and it is multiplied by this big term is multiplied by this one, which is e to the power 2ix. And notice that here the signs are reversed for pi2. It is negative or that negative. So that's why it will be plus, right? I sin 2x, I'm taking I sin 2x common. So there is extra negative staying here, and I'm taking the negative of that. So positive. Similarly, here negative I am taking outside. Here is the positive one. So since negative is taken outside, then the sign which will remain is positive. So e to the power 2ix, and again divided by 2 into 2i. 2 into 2i. This I will get cancelled with this I. Actually, this is a really great thing that this works. These cancellations will always work. This big term is multiplied for this one. The log is also having iota. Okay. Consider this big bracket. That's why I'm cancelling out. Then I is multiplied to big thing, whole thing. So that's why I could cancel it out. Okay. Now, what is this thing? This is cos 2x, and what is this thing? Sin 2x. So I will copy this big part because I need to see that whole thing in one slide. And notice that how big this has become when I use the fifth formula. Compared to the quadratic formula, this is really big. So that's why I will try to avoid this whenever possible, even though this works every time. So my particular integral in this case will be this cos minus cos 2x by 2, and this will give me sin x by 2, sin 2x by 2. Then this first whole bracket is sin 2x by 2 minus log sec 2x plus tan 2x whole divided by 2, and again this is multiplied with cos 2x by 2. Notice that I am having minus cos 2x by 2 minus cos 2x into sin x by 4. And here positive of sin 2x into cos 2x by 4. So they will get cancelled. They will get cancelled. The only thing that will be remain is minus log of sec 2x plus tan 2x into cos 2x divided by 4. And this is my particular integral. This big expression is my particular integral. Okay. I know this is quite well. Deliberately, I have taken a problem in which complex roots are involved. That's why this is taking a more longer time. For real root, it will take a little shorter time compared to this ones. You don't have to think about sin x, cos x, all those things. When I am having the real roots. In complex roots, you have to go for expansion again, then compressing them and all sort of things. Okay. So this is one of the difficult problems that can be considered of this type. Okay. Consider for the homework same thing. D square y by dx square plus 9y is equal to sec 3x. This problem is done in the notes. This is the first problem actually in the notes. If I fail to share the notes by evening today, you can refer this problem in the unaided batches of your classes. So CSA unaided and IT unaided, both the batches. This problem was discussed and above problem was given as homework in that class. Here you have their solved problem as homework. So if you want to compare the solution, you can and you can share this solution with them for their homework. Okay. So we'll stop here. And I'll say we have discussed a lot more things about the linear differential equations with constant coefficients. So whatever we have discussed was for constant coefficient. Only I will discuss one thing, one sort of things where I will have variable coefficients. So those equations, they do have again some simple looking form, particular form, and you can convert them into equations of functional coefficients. So that will be the content for the next lecture, which will be online, totally online, unless I am getting a class. If you can book a class on Saturday, just inform me so that we can take again similar version, online plus offline. Okay. Otherwise, the whole thing will be offline tomorrow or online tomorrow, in which only one substitution, the special substitution you need to remember for that one. How to convert that variable coefficient to constant coefficient by those substitution, and how to revert back your original solution. That's the only thing that will be there. Otherwise, everything will be used which was discussed in the previous lectures. Okay. So thank you. You can scan this QR to get the slides. Again, those who are online, those also. QR is shown. Thank you. We'll stop here. Welcome.